Hello, everyone. I hope everyone's having a great evening. My name is Jordan Bierbrier. Welcome to McMaster NEUDOSE Stars event. I'm just going to get my screen all set up. Anyways, thank you for coming out to tonight's event. My name is Jordan Bierbrier, and I'll be presenting on behalf of the Payload team. So just a bit of background information about the Payload team is comprised of 17 students and 2 principal investigators. Now, these principal investigators are Andre Hanu and Eric Johnston. Not only do they spend a lot of time working on the project, but they also bring a lot of knowledge to the table with them. And within the Payload team, it can be further divided up into firmware, instrument, electrical, and mechanical team. Now on the screen, what you can see is the CubeSat, what it's going to look like when it's fully manufactured. But before I get into that information, I'd like to give a bit of the motivation behind the project itself. So there's a rapid increase in space exploration nowadays, and evidently the space environment is completely different than here on Earth. But a characteristic that may not be so obvious is the radiation exposure. And if we want to continue to explore, we need to have a concrete understanding of what that radiation exposure is like. And so one of the goals that NEUDOSE has is to further understand the long-term exposure to space radiation, and that will be done by investigating how the charged and neutral particles will contribute to the human equivalent dose. Now, focusing in on the payload subteam, the payload contains a radiation detector, and the name is the Charged and Neutral Particle Tissue Equivalent Proportional Counter. Now, that is one mouthful, so what we do is we have a lot of acronyms, and the acronym for this is CNP, TePC, and they're prevalent throughout whole NEUDOSE, so you'll see a lot of acronyms. And we also have the DAM, and I'll be talking about both of these in more detail. Moving on to the instrument, the CNP TePC. This instrument is notable because it can distinguish between neutral and charged ionizing radiation. And the way this is done is using 2 different detectors, the TePC, which is that black sphere in the middle, and the ACD, which is the blue ribbon along the outside of the detector. And the way it's done, you can look at the screen on the left-hand side. Charged particle interacts with both of the detectors, whereas the neutral particle only interacts with one of the detectors. And we quantify this energy in terms of the lineal energy transfer, and that is the energy lost in an ionizing particle per unit wavelength travel. And this helps us determine how much charged and neutral ionizing radiation is absorbed by tissue. Now, I'll be focusing on the TePC first, one of the 2 detectors, and a part of that is the TE tissue equivalent sphere. This sphere is composed of A150 tissue equivalent plastic, and this material was strategically chosen as it has the same electrical conductivity and radiation absorption as human tissue. You can also see on the left-hand side of the screen, it has a thickness of 4 millimeters and a diameter of 48, so it's quite small. Next up, when a particle travels through the TE sphere, it deposits its energy, and this creates a voltage bias along that gold anode wire in the middle. And we're able to further process this signal and determine how much energy it deposits. Taking a step out and one level out, this the tissue equivalent proportional counter, TePC, is what you can see on the left-hand side. So it incorporates that TE sphere. It also has the preamplifier module and the high voltage module. And these are used to process the signal as well as power the TePC. And this sits within the pressure vessel base, which you can see at the bottom of the screen. And just to reiterate, we're measuring the lineal energy distribution. Now, taking another step out, everything you see in the bottom left is what we've already covered so far. And then what's included in the pressure vessel is this indium O-ring along with the pressure vessel lid. And now all of this is secured and closed up, and then we want to have it to a pressure of 40 torr and filled with a tissue equivalent gas, which contains propane, nitrogen, and carbon dioxide. And the way that this is done is we used a swage lock, which is shown at the bottom left-hand side, and we depressurize the pressure vessel first, and then fill it up with that TE gas to the desired pressure. And now the second detector, the ACD, or the anti-coincidence detector. And the way this detector works is ionizing radiation is absorbed by the blue scintillator, and it emits UV light. And that UV light is detected by the SIPMs, also known as the silicon photomultipliers. And those can be seen on the SIPM module, and that green board at the bottom of the screen. There are 32 of them. And these SIPMs have a resistor, and this which produces a photocurrent. Photocurrent is current induced by light, and this photocurrent is then converted into a voltage drop by the SIPM module. It's a mouthful, I know. And the point, just to reiterate, the amalgamation of these two detectors allows us to differentiate between a charged and neutral ionizing radiation. And the way this works, to get a bit more detail about it, is if the signal triggers both detectors within a coincidence time window width, it's deemed as a charged particle. And consequently, if it takes longer than this time window, this coincidence time window, then it's deemed a neutral particle. And that leads me into the next slide, which is the data acquisition module, and this is the brain of the payload. It does all of the communicating and powering all the components within the payload subassembly. It also transmits acquired data along with housekeeping data to the external satellite subsystems. And a concrete example of this is to digitize energy deposits from the detector. And just like from the previous slide, it also determines if an event is a coincidence, so if it's a charged or neutral particle. Now, the subsystem assembly, this is comprised of all of the components that I've spoken about so far, and it's mounted within the payload housing, which is in the middle of the figure on the left-hand side, and the TePC sits on it first, and then above it goes the ACD, and then below it is the wiring harness assembly, and that connects the data acquisition module to both of the detectors. Next is the mechanical interface, and this is the payload being mounted to the frame rails of the actual satellite, and joining all of the other parts of all the other different subteams will go underneath on the right-hand side. What you can see on the left-hand side is fasteners, and these are strategically placed, so the payload is never taking only shear. And also looking at the right-hand side, it can be noted that the payload takes up a significant portion of the satellite, and it has a mass of just over 1 kilogram. This slide demonstrates the electrical interface within the payload, and I really want to focus on the dam, which we spoke about recently. And it plays a crucial role in terms of signal processing and also power distribution. So the dam is located just in the middle, and the blue lines represent the signals, and they start up in the detectors and work their way down into the dam, and eventually go down into the bus stack. And then the power lines, which are the red lines, they're working the other way around. They start in the dam and work their way all the way up to the detector. Now, there are always really exciting and hands-on projects happening with the Payload Subteam. Currently, there are 2 test interface modules being done on the TePC and the SIPM, and these are to test and validate the components. before integration with the dam. We also have the Triumph experiment, and that is to test the functionality of our radiation detector under space-like radiation conditions. And this is done by shooting protons and neutrons at the radiation detector. And more on the mechanical side of things, they just sent over fabrication the pressure vessel, the ACD lid, the payload housing. And the really cool fact is that the TePC was actually made here at McMaster University. I want to finish off with this quote by Chris Hadfield. Remember, nobody changes the world on their own. This is a really meaningful quote, but I believe that it also perfectly aligns with NEUDOSE and their mission. There's a plethora of intricacies, many components, and a lot of documentation that goes into the project. And none of this would be possible if it wasn't for the team of individuals that come from all different backgrounds, but share a couple similar goals. A goal to learn, a goal to work hard, obviously a goal to have a functional satellite in orbit, but most importantly, a goal to have fun. Thank you for listening to the presentation on behalf of the Payload Subteam.